Hi there, this is our final video presentation for MECH2412. We hope you enjoy.
The project we were tasked with was to create a go-kart for the client, Canada's Wonderland, with certain requirements fulfilled. The model should be able to hold a 2 kg mass and be able to switch between high gear, low gear, and reverse gear. In addition, we needed to operate with a minimum turning radius of 5 meters or less, and travel up a 15-degree incline at a speed of 1 centimeter per second. As you can see, our design objectives were misunderstood. Many of the objectives we listed do not help us choose between multiple viable designs, but instead describe the requirements for any viable design. Most of the objectives listed here do not help us with finding the best of our designs, and so our objectives do not fulfill their purpose. Design objectives should follow more along the lines of speed, cost, or ease of assembly and use. Our list of requirements was well designed and was relatively well satisfied. We satisfied all but one requirement. Performance 3, which states that the kart should have user-controlled steering with a minimum turning radius of 5 meters. We cannot verify modularity 1.1 as the model is virtual, however the rest of the requirements can be verified by modeling in software. Our functional structure diagram was misunderstood and requires a rehaul entirely. The inputs and outputs should be materials, energy, and signal. Our inputs such as chassis, wheels, and transmission system should all be sub-functions under materials. Our entire system should outline all the functions and lead to base outputs of energy, materials, and signals with a clearer structure of sub-functions. The diagram should have helped us in identifying key structures to design, but this was not achieved.
After finishing the initial design of our project, we performed some strength calculations to better understand how the vehicle would perform. More importantly, it allowed us to see which areas needed improvement. What we found out was that one of these areas was the chassis of the vehicle and that the deflection of the chassis was too great. Instead of having to redesign the whole thing, we were able to compensate by using 2 layers of MDF and increasing the rigidity from the drive axle. Because of the added rigidity, the chassis wouldn't flex as much as it originally would, resulting in less deflection. Another area which needed improvement was the motor. From the calculations, we saw that the motor had a very large value for acceleration, meaning it was too powerful for the go-kart. Even though this sounds like a good thing at first because of the performance requirements, we realized that the go-kart would be unable to gain enough traction. We fixed this by implementing a 4-wheel drive system at the expense of an active steering system. While it would theoretically be possible to have both systems at once, our group had a lack of materials and decided that it couldn't be done. The final major area which saw a change was our group's usage of cantilevered shafts. At first, we had 2 of these shafts in our design. One was in the gearbox as an idler shaft, and the other was the main drive shaft. Based on the feedback that we received, we decided to scrap the usage of these shafts. Instead of having to undergo a major redesign, we decided to add supports and braces to our shafts, making them no longer cantilevered.
In this section, I will discuss and reflect on the morphological chart and conceptual design selection. The morphological chart can be seen on this slide. Selecting an option from each subfunction allowed for the completion of our 4 conceptual designs. The 4 conceptual designs can be seen here, along with labels that represent each option from the morphological chart. A noticeable problem with the first conceptual design is that the space for the functional components is undersized. For the second conceptual design, we ran into the issue of feasibility due to the tank tracks. For the third conceptual design, there is no 4-wheel drive and the wheels are not connected to a power source or drive axle. For the final design, the layout would not have worked because the transmission is located in the front. After reviewing our initial conceptual designs, our team concluded that none of them would work. The weighted decision matrix can be seen here, showcasing our best design at the time. However, because the client failed to disclose vital information, we were forced to make some design-defining assumptions. We implemented 4-wheel drive to account for the large amount of torque the motor produced. A custom-made power housing unit was also designed to optimize the layout of the components to meet the space requirements. Thus, a complete redesign had to be done of our conceptual design in order to reach our final design.
For our design, we needed parts to be functional, strong, and lightweight. We also wanted the parts to be visually appealing. This was a challenge. To solve this problem, we created an initial draft for each part. We then altered the part while maintaining integral solid bodies to become more aesthetic. Then we added support bracing to maintain the structural integrity. To create more visually appealing parts, we used organic shapes. Another challenge we faced was sizing the individual components. The motor sizing gave the team a starting point for the initial chassis size. Once the chassis was designed, we turned our attention to the motor and power housing unit. We started by making an approximately sized pinion gear to be mounted on the motor. Then we calculated the gear ratio we would need and created the remaining gears for the gearbox. Once the gears had been modeled, we were able to model the gearbox housing accordingly. The same procedure was followed for the remaining parts. Mating the gears also proved to be challenging. To properly mate gears, construction sketches of the pitch diameter were added to each individual gear. Tangent mates were then added, mating the pitch diameter construction sketches. Where the problem arose is that the gearbox had multiple configurations. Adding a gear mate only accounted for one configuration. Adding gear mates to all configurations over-constrained the assembly. To overcome this, we decided to use the physical dynamics feature instead of making 3 configurations. Upon reviewing the provided analysis, our team concluded that the analyzed parts were sufficiently designed. The yield strength of PLA is approximately 35.9 megapascals. The analysis showed us a maximum stress of 3.93 megapascals, which was for the pinion gear, and a maximum stress of 0.23 megapascals, which is for the payload holder. Both components had a negligible amount of deflection. This verified that the gears and payload holder are strong enough to withstand the loads and maintain a large factor of safety. The reason the gears are tested is that they're constantly under high stress and they can fatigue and fail over time. The calculations your crew performed showed that the strength of the components are acceptable, and the finite element analysis verified this. It is important to virtually prototype the design before physically implementing it, because it ensures that all the parts are functional and accurately sized. Designing the cart virtually also allowed us to identify and correct the flaws in the design, effectively reducing the cost of the project and the amount of waste material. Prototyping a design and then iterating without virtual prototyping would be a time-inefficient process. A final note is virtual prototyping tools such as finite element analysis allows the team to evaluate physical phenomena and verify the structural integrity of each component. This leads to a better product and improved customer satisfaction. For our final design, we made some minor changes. The first change was to decrease the number of fasteners. To do this, we replaced bolts for extruded tabs that feed through the mounting holes in the chassis. The bolts were then strategically placed to secure the component to the chassis. The second place we remove fasteners is on the gearbox cover. To remove the fasteners, we removed the bolt holes from the gearbox, extruded tabs in the 4 corners of the gearbox, and then added flanges to the lower section of the gearbox. This allowed us to use rubber bands to secure the cover to the gearbox. The third and final change we made to the prototype design was implementation of gear keys. We forgot to add these keys to the prototype design. The keys stop the gears from spinning on the shafts, allowing the gears to transmit power to one another.
Thank you for watching, and we hope that you have a good day.